All right. So, first thing, thank you everyone for the opportunity to speak to you. I do wish I could be there in person today. That had been the original plan. In fact, we were going to do this last year, but some circumstances prevented that, and I've got to go to Europe this afternoon. So, unfortunately, I had to be here in San Francisco, which is where I'm based. Um, so for those that probably don't know me, I lead the product development organization at Autodesk for our design and manufacturing solutions. So why don't I'll share my screen and we might as well get started. Hopefully you can see the presentation. Is that
Yes.
coming through? Perfect. Okay. So I lead product development for what we call design and manufacturing at Autodesk. So by design and manufacturing, we have a portfolio of tools that are focused on 3D modeling for mechanical design, electronics, simulation for linear statics, etc. And then we have a range of tools for manufacturing. So we're also focused in subtractive manufacturing and additive as well. So my organization runs product management, XD, and software engineering for that group. So um, I've worked in a number of positions across Autodesk. So I've also run our strategy team as well. And I'll talk a little bit about the role and influence of strategy here in a moment. Originally, I was a mechanical engineer. As you can probably tell, I was based in the UK. I got into software later in my life. I actually got into software because I was a mechanical engineer really at the point 3D modeling started to become like prevalent across our industry. And I ended up working for Autodesk to actually support the product. And I've been here, for the last 20 years. Great place to work, by the way. If you're ever interested in an internship, you should reach out to me. Um, I do also believe in lifelong learning. So I went back to college and did an undergrad in software in my 30s. And believe it or not, I am in the process of learning again. In fact, I've just finished my executive MBA with Cornell. So big fan of Big Red. I'm really honored to be able to speak to you all today. So thanks for that opportunity again. So really the subject this morning that I wanted to cover, or this afternoon for you, was systems engineering, obviously relevant to many of you in the class. But I do like the fact that there's a mix of people here. So you mentioned there were folks focused on mechanical, electronics, or electrical, as well as software. And that really is the kind of key to systems engineering and why we think it's so important. So I'm going to give you like the Autodesk view on this. I'm probably not going to teach you a lot that you aren't already learning academically, but I can at least help you understand a little bit more about the relevance in industry. And I also want to explain to you why I think it's so important for your careers moving forward, because this is an area of huge opportunity that's probably on the cusp of getting redefined or disrupted by some new technologies that are coming to market. So that's kind of the objective for the session. I believe we've got about an hour. Is that correct? Hopefully. Yeah. Okay. So obviously I'll stop for questions if people have got them, but I'll try to make sure we leave some time at the end. So if you don't know, Autodesk focuses on three main industry verticals. So we focus on what we call the built environment. So that includes things like civil engineering, building engineering, architecture, all sorts of different technologies in that space. The reason I mention this is that each of these industries involves a heavy amount of systems engineering because systems are really just a abstraction for models that would otherwise be too complex to calculate or consider in their entirety. We also operate in the media and entertainment industry, so that's films and games and TV. Again, systems tools are employed there to manage some of the assets that run across a production environment for a film like The Martian that you see here, or any of the sort of AAA games that come to market. So most of those are developed with our technology. But of course, the group that I'm responsible for is design and manufacturing. So for us, that largely focuses on what we would call discrete product manufacturing. So individualized products. They could be automotive vehicles, consumer products, building products, or large-scale industrial machinery. So that's the area of focus. What makes Autodesk kind of unique is that we span those industries, and while they might seem separate to one another, they employ a lot of the same technology. So you can imagine the rendering and visualization tools that are used in media and entertainment are also highly relevant for visualizing products in manufacturing. And actually, when you look at how we build products, our products too rely on systems modeling. Obviously, we build cloud technologies on a cloud platform, and we have to have pretty extensive systems engineering to understand load balancing and the impact on the various components that we use to compute some of these products. We're also big into education. So we're big partners for Cornell. We also believe in making technology freely available to anyone. So if you aren't aware, our entire portfolio is completely free of charge to anyone who's an active student. So you can go on to autodesk.com. Any of the products that we've got, whether it's in building, electrical, mechanical, visualization, machining, and manufacturing, you can license any one of those products under a student license completely free of charge. So if anything I talk about today is of interest to you and you want to experiment with it, then just go on to .com, autodesk.com, and have a look. You should be able to pull it for free as a student. And again, if you have any problems, just reach out to me and I can put you in contact with the right people. Um, so like I said, my focus today is on what we would call design and make. So one of the things that makes Autodesk, again, unique, one of our competitive differentiators, is that we are focused on unification between design and the actual process of physically producing an asset. So in architecture, we look at the building's definition and design, and we see it through to construction. In films, we look at asset development all the way through to media production. And in manufacturing, we do industrial design, mechanical, electrical engineering, simulation through into manufacturing on the shop floor. And the reason we do that is because of the increased level of complexity, not only in product definition, but also in the manufacturing processes that are employed. And our belief is that new forms of manufacturing have a heavy influence on how you design. So most 3D modeling tools, if you use them, will be somewhat familiar to you if you understand subtractive manufacturing. So they use a process of Boolean modeling to subtract bodies from one another, very much like a machine tool subtracting material from a piece of raw stock. And so because of that relationship, the modeling system is kind of optimized for traditional subtractive manufacturing. And as a student, you're usually taught in mechanical engineering that any time you make a modification to raw material, every time you remove material, you're introducing cost. So that influences how you think about design. Additive manufacturing is actually the reverse. Every time you add material, you're introducing complexity because you're printing, not subtracting. And so our belief is that the design tools need to reflect the manufacturing process if you want to automate these processes and drive bigger productivity. So we've invested in our own manufacturing facilities. This is from our organization in Birmingham in the UK. If you're ever in the UK, you want to take a tour of this facility again, reach out to me and I can get that set up for you. We also have a facility like this in Boston as well. So again, if you're ever in one of those locations and want to take a look, let me know. Our belief, our belief is that, by using the technologies and actually employing them, by doing work for our own customers, it helps us better understand how the technology works. I think you'll also find in most curriculums now, there's a much heavier emphasis put on not just designing, but also seeing the project through to manufacture. And that's something that many professional organizations follow these days as well. So strategy, why does it matter? Because whatever you do in the world of product design and manufacturing should be driven by what's going on in the market if you want to be successful. So our view is, and this is good news for you all, that in manufacturing, there's a huge skill shortage coming. So I'll talk a little bit more about why we think that and the implications in a moment. We also think that there's a dramatic rise in cost. So a lot of the global macroeconomic conditions that are being caused by some of the politics that are going on also have an impact on things like material and energy costs. And then the last one is supply chain disruptions. So we can talk about those in a bit more detail, but what technologies do we think can solve those? So in the area of skill shortage, we actually think smart product definition and AI is going to be a big influencer in this area. In terms of rising costs, digitized processes are usually the answer to that. And from a supply chain flexibility point of view, we think cloud connectivity has the biggest influence in this area. So if you look at smart products and AI, our belief here is that products are becoming increasingly complex. So this is a trend that kind of started with phones. When you say a smart product, you instantly think of a smartphone, modern day cell phone with, web connection, email, etc. But that trend is kind of proliferating across the rest of the built and manufactured product industry. So, if the next big area of redefinition was probably in the automotive market. So, as you move to electrical systems um, in EVs, software is obviously the key driver there. So, most cars, I mean, mechanical cars didn't have any CPUs. Most sort of modern cars had one or two. The average EV has up to 27 separate CPUs. So obviously a lot of complexity in terms of software engineering. And that trend's continuing. So on the right there, you see a controller from a Mazak machine used for subtractive machining. And traditionally, these controllers were very kind of 1970s, 80s based with punch buttons. You can now see that they're becoming largely software driven. And we expect this trend to continue everywhere. And there's more and more smart devices wherever you look. And more of these are going to be influenced by investments in AI. Digitized processes. So in manufacturing, the move towards digitizing processes has kind of continued since the 1980s to the point now where just about every manufacturing process employs software. The problem is it employs lots of different software, so it makes it very difficult to connect the process. And of course, when you manufacture a product, you don't just use one manufacturing process, you use a whole range of them. So being able to model the system in that environment is also important. And then the last one is flexible supply chains and logistics. So from a logistical sense, that too is a system. So you have a system of suppliers that may be distributed geographically, and you need to be able to model the impact on those suppliers if you want to run a sustainable business. Because if you don't have a view of that system and the impact on your manufacturing process, you can quickly run out of inventory in the middle of a production run, which obviously can be a big problem. So one of the drivers that we see for this is a lot of different technologies and software are used across the manufacturing process. So just in sort of R&D, first article production and design, you could be looking at a range of tools like SolidWorks, Rhino for industrial design, KeyShot for visualization, SolidWorks for modeling, maybe Altium for electronics design. And then when you go into manufacturing, it gets even worse. And the problem is that each one of these tools stores information in a proprietary format that only relates to its individual discipline, which is task-based. So 3D modeling, mechanical design, Altium for PCB electronics design. And so you're not able to get a reasonable view of the overall systems architecture. And that should include manufacturing too. And so we see three core barriers to this for customers. The first one is that the data is abstracted and stored in proprietary formats, so boundary representations in models, which are stored in tools like SolidWorks in a parasolid body. You have 2D documentation, traces for electronics, schematics, bills and materials. None of this information is easily updatable. So if you make a change to the 3D model to propagate that change, you need to then go into the manufacturing system, open the proprietary file format, import it, update the manufacturing process, save it, move it on. It's a very waterfall process and in an environment that really should be moving towards agile. The second is, and I'm sure you've all experienced this, when you use these different task-based solutions, they all have different user interfaces. So it makes it very difficult to learn how each one of these tools work and then how to pass information through them digitally. And then you need a PhD to really understand all of the different technologies in the market, how they relate to one another, and how you would build a single, consistent, cohesive digital thread through your organization. And the same is true for Autodesk. I mean, we have a massive range of different products in our portfolio today. So our goal has been on converging all of our technologies into one single cloud platform that we call Fusion. And the idea is that you build a single digital model that's open and extensible in a graph. Now, a graph allows us to actually create a systems level representation, not just of the mechanical or electrical design, but its functional characteristics, as well as the manufacturing process that's used to produce it. And that will ultimately enable us to better model and optimize those product designs and their manufacturing processes. So I'm going to come back to that a bit later on. So Fusion today really focuses on the process of taking a mechanical design, industrial styling, electronics, simulation, and manufacturing. So I wanted to give you a little flavor for this because it's kind of foundational when you want to start thinking about systems architecture for a complex product. So this particular example is from a company called One Click Metal, who are a startup organization making an additive metal 3D printer. So this is Fusion. The idea is that in Fusion, you can work with data from multiple sources. So it can be SolidWorks information, or it can come from Inventor or ANSYS. And the idea is that you can aggregate that information as well as creating information here natively. If data in SolidWorks changes, it updates here. The important bit, though, is that it supports multiple personas. So you could be a mechanical engineer doing sheet metal in the top left, or an industrial designer doing some styling for the cartridges that go into this system on the bottom right. In fact, you could be, an electronics engineer as well, creating the schematics and control systems for the product. The important point is that when teams work collaboratively together, they're accessing the same set of information, which represents the overall system. And they're able to collaborate in real time. So a bit like Microsoft 365, you can see all the different users and the different product areas that they're currently working in. So the idea is that you can be concurrently engineering together as a team. So if you're in the electronics environment, you can start with a schematic. You can start to do some analysis of signal integrity across that schematic. You can lay the board out. You can calculate the traces. But because we have a single digital representation in the background, we can convert the 2D board layout and its traces to the 3D representation. And that enables you to go through into a simulation environment so you can start to look at, convection cooling across the surface of those boards to make sure the CPU doesn't overheat, for example. The last phase is manufacturing, probably the most important. So in this case, you can take the guarding and you can say, okay, extract all of the 14 gauge or 2 mil thick mild steel, schedule it for production, nest it, take it through to a manufacturing environment in the same platform, and then tool it. So you can choose, in this case, a plasma cutter, and it will calculate the tool paths for you, simulate that, and post-process the information so you can send it to the shop floor for manufacturing. So that's the idea for Fusion. And as you can see, it's covering a lot of different disciplines. So that creates a problem because as products get more and more complex, they involve more and more disciplines. So just in this simple example from a consumer product, there's electronics, mechanical design, styling, wiring, PCB, CPU, chip design. And of course, that gets very complex, and you can't get an idea of the overall product's functional performance characteristics by just 3D modeling it or by just looking at the schematics for electronics, for example. So it's becoming an increasingly complex system. And so, what do you do when you have a complex system? So, look at a city, London in this example. There's a transportation network. If you consider the whole model in its full detail, it becomes overwhelming and you can't optimize any part of the system because it's just too much for anyone to account for at any one time. So you go through a process of abstraction. So one of the best examples of abstraction is the London Underground map. It's simple, it conveys only the information that's required, and it allows you to gain a much better understanding of one of the potential subsystems. So that process of abstraction is something that's pretty common across all creative disciplines. So, for example, if you look at process plant, electronic, software engineering, or factory operations, every one of these industries employs a level of abstraction. So if you think about process plants, they have what they call P&IDs. So P&ID is just simply an abstraction of the higher order system for a petrochemical plant in this case. if you look at electronics, they have schematics, which is our higher order abstraction of the overall function for a circuit board in this case. In software, we use UML diagrams to create structural diagrams, class diagrams, or sequence diagrams that, again, let us abstract the system and do black box optimization. And even in factory, there are process models for the production that allow us to do our operation studies and make sure that, we're looking at a specific set of characteristics and optimizing them. What I would say about MBSE is that it's pretty unique in the fact that it starts to combine these higher order abstractions into a complete systems view. And the opportunity here is to extend that. So it's not just electromechanical, but also considers the manufacturing process itself as well. So that's one of the areas that we're focused on. I did want to give you a bit of an example here as well. So if you think about higher levels of abstraction, and I mentioned supply chains, Amazon's a great example. So in this case, what we're looking at is an Amazon distribution logistics center. And so you can imagine in one of these centers, it's extremely complex to understand and model what's going on. You've got hundreds of thousands of products. Same's true in a hospital where you're processing patients. Again, logistics centers can be incredibly complex. Any shop floor operation where you're processing equipment and manufacturing products involves a whole array of different subsystems, including people and machines that are often unpredictable. And so you can't deal with that level of complexity when you look at the entire system. You need to be able to abstract to a lower level of detail. So, in the case of operations management, is there anyone that studied operations in the room? Q theory, anything like that? No. Okay. Well, this will be relevant, but maybe not so interesting. So when you look at how a factory operates, there are tools, mathematical formula that you can use to evaluate the flow of inventory. So there's a thing called Little's Law, which basically looks at queue processing and queue management. There's a VUT equation that you see here, which helps you understand the impact of queuing. And if you pull multiple operators in a queue together, how you can increase the flow rate in a production process. The problem with this is that this is also quite difficult, and you're looking at a particular slice in time. So you're not able to evaluate the system with continuous flow with multiple lines and how they interact with one another. So that's an ideal opportunity for systems-based modeling. Okay, so this is a good example of being able to abstract a system and model it. So in this case, what we've got is a source and a sink. So the source is where inventory is coming into the process. There's three machines that need to operate on that. And then there's a sink, which is the finished article that's going through the process. So in a layer of abstraction like this, what we're able to do is start to simulate behavioral characteristics. So we can connect the source across to the machines. We can also tell the source that it has an operator. And so for this source, we'd like this human being to carry the inventory for us. And so when we do this, we can actually run the analysis and start to get not a singular slice in time. So let's make this, I want to speed it up so that we're not waiting too long. So rather than a single slice in time, what we're getting is like a continuous evaluation for the whole process. So you can start to see the operator processing products, and we can graph that data because it's an abstraction. It makes it easier for us to graph the data. So you can see the operational utilization for each machine. So in this case, we're reaching about 50% machine utilization. Which isn't great because if you've invested millions of dollars in your plant equipment, you want to make sure that you're optimizing the machine for the best utilization so that you have the highest flow rate and manufacturing process efficiency possible. So you can see here that we're kind of yielding 16. If I run the simulation all the way through to its conclusion, we're probably processing somewhere in the order of 1,100 products in the time, and we're getting an average kind of process efficiency or utilization rate of about 45, 48%. So the thing about systems models is that they let you start to optimize what's going on in this model. So again, if I come back and I'm going to break the links here, and I'm going to stop and reset the model. And what I'm going to do is introduce a queue. So a queue is going to act as a buffer. And so now I can connect the source to the queue, take the queue and connect that to the machines. And then I'll also connect the queue to the operator again and tell it to use that operator and stop and reset. And now I'll just change the timing so we can watch what happens a little easier and then run this simulation. And what you'll see now is something slightly different. Because there's a buffer, we're allowing the inventory to stack up. And so there's still a single queue to the 3 machines, which is optimal. But now look at the utilization rates on each one of the machines. The utilization rates are actually going up and up. So now we're up into the sort of early 60s. I'll guess that when we run this through, we're going to end up with utilization rates in the sort of mid 70s. So here we go. As it runs through, you can see we're up to 70% And when we complete the simulation, we've got a mean processing time or utilization rate, sorry, of about 75%. And the throughput now has gone from 1,100 products in the same space of time to 2,100 products. So I realize not everyone in the room might be interested in operations management. Actually, you should be, because if you're going to go into manufacturing, I can tell you the fastest way to fail in manufacturing is to design a beautiful product that can't be made cost effectively. So your job as a mechanical engineer, for example, or an electrical engineer, is to create a product that solves a market problem. But above all, it's to make that product profitable. So your job as a mechanical engineer is actually ensuring product profitability and accuracy, and these types of tools help you do that. The problem is they do it in isolation. So you're not getting a view of the entire system. So in this model, what we've done is for each machine, we've calculated the mean time for processing, and then we have some statistical data, the standard deviation of the arrival time, the processing time. And from that, we can kind of model out what we expect the factory flow to look like. But of course, there's a subsystem for the machine itself. And so you end up with this nested set of systems and subsystems, which is really the future, I think, of what you'll see in design and manufacturing. Hopefully that kind of helps you understand why abstraction of a complex system can help you model a particular characteristic in isolation, and that can let you optimize the process. Because really, MBSE is all about optimization of process. But like I said, that process is getting more and more complex. It's introducing more and more different processes or steps in the process. And it shouldn't be completely isolated to just design disciplines. So as I said, the product that we just showed you there for manufacturing execution analysis is a tool called Flexim. But there are CAM tools. You need a CAM tool to be able to model the process of machining a part or printing a part. There's electronics tools. There are simulation tools, but there are also business processes that sit around this. There are math modelers like MATLAB or Wolfram that help you look at the overall formulaic principles for a particular product. So those product behavioral characteristics are the things that you're seeking to model when you're using a systems engineering environment. But the business process is just as important as part of that. So you can see an expansion actually of these systems. So you could take an average product to market, an average consumer product, and you would need to use something like Cadence for electronics. You might use a requirements management system. You'll need a CRM system to sell it, like Salesforce. You'll be building software that'll need to run on a platform like AWS. You'll need to model the overall behavioral characteristics with something like Mechanica. You'll need to manage requirements, visualization, manufacturing, sourcing of the materials, simulation, the software elements, like maybe some code in Python. You'll need to model the support process. So being able to model this complex environment is way too much information to process at any one particular level. you also, as a mechanical engineer, need to watch out, not just a mechanical engineer, any form of engineer. One of the biggest issues you need to watch out for is scope creep. So scope creep will happen as you take a particular set of market or customer requirements. In software engineering, we talk about did you build the software right? And did you build the right, or do you build the right software? And they're two actually different questions. So building the software right is making sure it's performant, it doesn't have bugs, it does what you need it to do. Did you build the right product is a question of, did you maintain accuracy with respect to the market requirements? And so those two questions sometimes get misaligned. So as you go through the process, you can sometimes become so focused on the product design that you start to get scope creep and actually violate the original customer or market requirements. And this is very, very common. So you'll come across something called a V model. If you haven't, I would imagine that you've probably studied this in systems engineering. If you haven't, you probably will. And I would definitely advise you to kind of get familiar with it. So the V model really talks about continuous validation and verification across the process. So it starts with requirements as an input for needs analysis. You then get to a requirements definition that's at the architectural level, system design, and then you get down into detailed implementation. The point is that as you come back up through the V model, you are continuously evaluating what you built back across to the customer or market requirement, so that you can be sure when you're busy 3D modeling some mechanical aspect of the design, which has an influence maybe on cycle time for a subassembly, that any decision you make there doesn't end up violating the original customer requirement. Hopefully that makes sense. So, you know, a product like a piece of industrial machinery or a car is very complex. If you're Elon and you're coming to market and saying that the most important thing about the Model S is that it's the fastest road vehicle in the world, and for that to be true, it needs to have a 0 to 60 time of 1.99 seconds, you need to be continuously evaluating every detail engineering choice that you make back to that requirement. Otherwise, you'll spend billions of dollars developing a vehicle that doesn't satisfy the original requirement you wanted to go to market with. So this is really a question of connecting product management back to detail engineering and using systems architecture to do it. Great example of that, complex system like an airplane. So you can imagine all of the different sub-assemblies, and this comes from a company called Medellin that uses a language called Medallica, open source language, which enables you to model component architecture. So you can build a black box that represents a hydraulic pump. That black box will have a formula that tells you what the transform function is between the input and the output of the system, so that you can then start to build together a multidisciplinary system where inputs from one domain discipline like hydraulics can form inputs to another domain discipline like mechanical systems in the landing gear. And so that enables you to create multiple layers of abstraction as you move your way down from the overall architecture into the individual detailed disciplines. And so that enables you to do what I described earlier, which is to go from the behavioral characteristics through a parametric definition into verification, while you go from system to subsystem to part level definition. So that's kind of the key about what we're talking about here, is being able to model that. So at Autodesk, what we're trying to do is develop the foundational data structure to do this. So we use a graph-based modeling system. And in a graph system, we're able to store information in a database that's relational, and we can open up that graph to include all disciplines of the design. So what I wanted to get into next is where this is going in the future, because I think this bit's really exciting. And this is the bit I want you to start focusing on, because I think it's going to be really important to your careers as you move forward. So the last 30 years, the software engineering tools that have been used to describe products and manufacture them have been what I call task-based. We mentioned that at the beginning. There's a CAD tool, a CAM tool, simulation tool, a data management tool. The information is all stored in a proprietary format. We then talked about how these systems are converging so that we get one digital model representation of the product and its manufacturing process. Our view is that that's going to lead to disruption in the market in the form of what we call generative design, but intelligent automation. So right now, you're going to be hearing all sorts of stuff about generative AI. A lot of it's true, and it is going to be massively disruptive. It's in a bit of a hype cycle right now. Most of it is focused on text-based prompt. Some of it in visualization. You're starting to see generative AI for video, for example. We think it's going to have a massive impact in design. And so we've been planning for this for a little while. First thing we did was converged all of our technologies to create a single digital platform on which you can model 3D geometry, electronics, etc. Second thing we did is we built that open graph model for modeling a complete product. And now what we're starting to do is focus on automation. So this is why a systems level representation is going to be important. It means that if you understand the manufacturing process, you can start to automate the process of developing the design based on some functional characteristics. So this is a quick example of generative design. In this case, what we're doing is specifying some elements of a design that we would like to remain. So these are the interface points in a particular design. Then what we can do is specify some design conditions. So we can say, there are certain elements of the design that need to remain fixed. There are some structural loading conditions. We can define some areas of the design we'd like to avoid. We can also talk about what the optimization characteristics are. We want to optimize this potentially for a factor of safety of 4, say. We can also tell it the manufacturing process because we understand the systems representation of also how this product will be made. And then with that information, we can start to generatively define a range of different options for the actual mechanical design. So as an engineer, your job is really just to make the right trade-off decisions to get the optimal part. Maybe that's weight versus factor of safety, or factor of safety versus cost, or cost versus weight. So you can start to make those trade-off decisions. And again, this is about building a product that's functional, cost effective to manufacture, and highly differentiated from anything else in the market. And so generative design enables you to automate the process of creating geometry like that. Doesn't mean that you won't go and edit it as a designer, but it does mean it's going to be a powerful tool for you as engineers to optimize and manufacture products. Then you get into non-value added tasks like machining and drawing. And so we've been working on areas of AI to help us take models that are produced in systems like this and remove the need to actually create documentation. So in this small example, what you'll see is that we're basically taking the design, adding a couple of dimensions, and then we're asking the system just to create all of the detailed documentation for us and scale it. So the thing I'm emphasizing here is that the focus for mechanical or electrical engineering, it historically has had a lot of focus on building 3D models and adding dimensions to them to communicate them to the manufacturing floor. Our belief is that this is going to change with AI. So these lower value added tasks where you're really just creating documentation or building a 3D shape is really not what mechanical, electrical, or systems engineering is about. The whole process of engineering is about taking a set of requirements, making the right trade-off decisions for the most cost-effective products you can bring to market to solve those requirements that's differentiated from your competition. So any time that you spend creating documentation or machining a part, for example, is wasted time. So in this example, you've got another 3D model, you need to manufacture it. So I often say to people, you're taking notes on your laptop. Imagine when you got home, if you had to spend as much time programming your 2D printer to print that document as it did for you to write it. You'd think that was crazy. And so that's what we're changing here. Here, what you can see is we're automating the process of taking a 3D model and building all of the machining strategies necessary to manufacture it. So we can play the simulation back and you'll see the stock material removal. And basically, you can go from the raw material stock all the way through to the finished part. We will also optimize the cutting parameters with AI. So what you'll see is that as we go through the process of deciding how deep to cut and how fast to cut, there's a trade-off between breaking tools or not being as operationally efficient as you would like. And remember, go back to my factory simulation earlier as a subsystem. The cycle time on this machine is what tells you the flow rate in the factory. So those two subsystems today are disconnected, and that's really what we think the future of MBSE will be. It won't be you as mechanical or electrical engineers making shapes or teaching machines how to make the shapes that you just made. The future will be you really focusing on the core engineering principles that are contained within this graph. So we actually foresee a future where you will set the requirements on the left. And I've just put Excel in there. There's lots of sophisticated systems like doors that will help you catch and market and customer requirements. We think it's possible to take AI, convert those systems requirements into a high-level systems architecture. Then we think we can automate the process of taking each element of that systems architecture and moving the data to the detail engineering discipline, whether that's mechanical design, electronics, simulation, or manufacturing. And this is what we think the future will be with systems engineering, is I'll bet you in 10 years from now, the product development industry has changed, just like the software industry has changed. And you as engineers will spend your time on the systems architecture, not details. And I can tell you that's happening in software right now. So you've seen with ChatGPT that you can actually get it to write Python scripts. So you can actually get it to write C++ for you. Microsoft's implementing that with Copilot. And so software engineers that have spent their entire careers building domain expertise in writing classes to represent objects are now starting to be very concerned that tools like ChatGPT are going to basically replace their jobs. And so you can see that the skill set will just transfer. We think the skill set will transfer to the overall definition of the system, not the detailed implementation. And that's nothing to worry about. Like I said, there's a skill shortage. I think the Bureau of Labor Statistics says just in manufacturing, there's going to be 2.1 million unfilled jobs by 2030, sorry. The same thing's true in software. But what it does mean is it means the skills that you're learning, you need to think about that now and to find the right set of skills to develop to meet the future, not the past. And I think that's what I really wanted to leave you with here. The first thing is my advice to you, and I've been around in this industry longer than I'd like to admit. And when I was your age, our whole focus was on, building 3D models that satisfied mechanical requirements and validating them and creating the documentation for them. I think the future that I would suggest is the best place to spend your time is on product architecture, not the artifacts. The artifacts are 3D models and drawings and schematics, etc. As a mechanical, electrical, software, or systems engineer, you're focused on the product architecture, the the solution to the market requirement that you're trying to build that's cost effective, not the detail. The second thing I would say is diversify your study as much as possible. I was lucky working at Autodesk that I got to work in lots of different departments. I went back and did software engineering. Like I said, I've just been back to Cornell to do my exec MBA. So I believe firmly that you want to keep learning through the whole of your life. I also think at an undergrad level or even postgrad, if you look at how human progress has evolved in the creative areas of, you can look back and you can say there was a period of time that was called like the Renaissance, right? And in the Renaissance period, people learned lots of different disciplines. And the beauty of that is that you could innovate because you would take a concept from one area of study and apply it to another. And we kind of lost that for a while because we went into detailed domain knowledge. So people would study a particular discipline and become absolute experts in it. I think what you're about to see with some of these technologies that automate those detail areas of discipline is there'll be a return back to a kind of Renaissance period where you do want to become multifaceted. You're going to want to know some Python scripting, some software engineering. You're going to want to know about how an electronic circuit board's made and how to design one and how it can drive hydraulics, pneumatics, or mechanical systems, because that's going to be the future, is to focus on the architecture, not the detailed domain discipline. And then the last thing I would say is explore some of these emerging technologies. If you haven't done it, I'm in the process of doing it. I'm trying to get back up to speed on my Python. I haven't done that for a little while. Python's great because Python's the tool of choice for people that are working in data sciences like machine learning. So I'm actually going to go back and do one of the certifications with Cornell on machine learning pretty soon. I would encourage you to do as much of that as possible because I think over the next decade, you're going to see our industry rapidly evolve. Building new skill sets in these areas is going to be hugely beneficial to you when you're out there in the industrial practice, in the sort of corporate world. So those are the three things that I guess I would kind of leave you with. I think the area of model-based systems engineering is possibly one of the most exciting. I'm a mechanical engineer. I've learned software. I love MBSE. I think it is the future to abstract problems and then to apply things like machine learning to optimize those domains. That's absolutely where you're going to build products that differentiate in the market. So yeah, those are the three things I would leave you with. Again, if you're ever interested in anything we do at Autodesk, you want to get access to any of our software, you want me to put you in touch with somebody, just reach out to me. My email address is just my name, so stephen.hooper@autodesk.com. Probably the easiest way to reach me. Sometimes it takes me a bit of time to get back to folks, but if you ever want to reach out, please just let me know and I'll be more than happy to help you. So finished a little bit early. I don't know if there are any questions.
Any questions for Stephen? Do you have one?
Yeah, please. One of the things about products getting more complicated is we seem to throw them away when they break. And in the old days, we had stuff that sort of lasted for a long time and you could fix it. Is there any is that incorporated into the stuff you're talking about?
Yeah, absolutely. I mean, that's a topic. I mean, that's becoming very topical right now. So it's funny how some of these trends kind of come around and go around and get new names. So, when I was studying, we used to call it reverse logistics. So reverse logistics were, I don't know, Cisco was a good example actually. So routers, what they would do is as soon as the technology became out of date, there would be trade-in programs to reclaim the old out-of-date tech so they could reclaim things like circuit boards, chips, resistors, they decompose them. That's still prevalent today. That's why folks like Amazon will do trade-ins. Apple does it, right? So they'll take your old products and recondition them to use the components in new products. But there's now a sort of growing trend toward design for circularity is the term for it. And again, I think this relates quite nicely to the topic of systems engineering because systems engineering is really about modularity. And so, in software, day one lesson is you want to create a system in which the components of that system are as decoupled as possible. So that's basically designing for modularity in a mechanical engineering or electrical engineering environment. So benefits of that is you can remove one component from the system, plug a new one in, and as long as the interfaces stay the same and they're decoupled, the entire system ought to be able to continue to operate, maybe with some optimization. So the same's true in any design discipline. You can design for modularity, like the building industry is going through this right now. They use a term called industrialized construction, which just means taking manufacturing principles, decomposing a building into sub-assemblies, and then manufacturing them off-site, bringing them on-site to assemble them, and it's much more efficient. So I think that kind of design for modularity is what you get when you systems model, because in systems modeling, you're decomposing into component technologies that are connected together. If you can do that, what you can do is then, design your product for circularity so that it's upgradable. Like a PC is a pretty good example. That's a system that's composed of a CPU, cooler, motherboard, GPU, power supply. Nice thing about a PC is you can upgrade it. And so you don't just throw it away. Obviously, there are components that you throw away, but hopefully the manufacturers take those back and then they themselves decompose those into smaller levels of granulation. So I think that's really something that's very topical at the moment. Certainly something in Europe where there's actually legislation being brought into effect to encourage manufacturers to adopt circularity in their manufacturing process. There's actually some pretty tight legislation coming in to control emissions from manufacturing plants, but also, at the back end of the process, the consumption of the products by consumers. So I think you're going to see more and more of it. I do think it's our responsibility to drive that. And as a next generation of engineers, I'd encourage everyone to think about that. Every day you see news about climate change and the impact of consumerism on our environment. And I think it's something that as a human race, we seem to have buried our head in the sand for a while. I think people are just starting to wake up to it. And I think as engineers, you're perhaps in the most influential position. I think the two industries that can do the most are, engineering and building and construction. So I don't know if that answers your question, but yes, you can Google design for circularity and you'll find a lot of information on it.
Stephen, thank you. This is Eric Gensch. I'd like to ask you a question about time. So if I use an aviation example and we rewind the clock about 80 years, at that time, the world's most advanced fighter aircraft was designed in about 100 days. Today, obviously, it takes a decade or so to design an advanced aircraft. Do the technologies that you're working with offer any promise to reduce the time from concept to fielding of complex products?
They do, but it's a trade-off. So, with complexity, you pay a price for time, and you're just continually trying to use technology to offset. So a good example would be CPUs. So chips, integrated chips, obviously in their first sort of rendition were human designed, but they quickly became so complex that humans can't design them now. I mean, there are millions, if not billions, of transistors on it squeezed onto a single chip. And so they went through a process that I'm talking about here for mechanical, electrical, and systems engineering. They went through that process a decade ago, which is what they would refer to as synthesis. So they take a set of input requirements, use not always AI, but certainly automation techniques to synthesize a design that the human doesn't build. So in fact, actually, companies like Cadence, who are at the forefront of that, are investing like crazy in AI right now because they think that that's the offset to get to the next generation of chip. So I think to your example of aircraft, if we were to design the same aircraft we designed 80 years ago, we wouldn't take 100 days to do it. We'd probably take a week or two. The problem is that the aircraft has become more complex and it's yielded better performance for sure. So it's always a trade-off between performance increases complexity, increases time, and then you can try and offset that with technology. And there's been a lot of studies on the implementation of technology and how productivity is kind of plateaued over the last decade. You would have expected productivity to have increased as technology adoption had increased, and it's not, it's plateaued. But I actually think that's probably more a consequence of the complexity of the products that we build offsetting any productivity gains. So I think the upshot of it is, as engineers, it's very important that we stay up to speed with these automation technologies, because the danger is if, as an organization, whether that's a country or a corporation, if you don't stay up to speed with this, you're at a competitive disadvantage. And so as the complexity increases, you'll either lose your ability to compete functionally, or you'll lose your ability to compete cost effectively. So I don't know if that answers your question either, but I would say if we were to build the same product, yes, productivity would definitely increase. But unfortunately, we're in a position where we're constantly increasing complexity.
Excellent, thank you. Any other questions for our speaker today? Stephen, congratulations on getting your Cornell degree. Well,
I haven't got it yet. I don't, commencement isn't until the end of May, I think. So,
Okay, you're almost there. We'll see you across the finish line.
yeah.
Thank you so much for your time today. Thank you for Autodesk support of the academic community. We'd love to give you a boxed lunch, but unless we can get DoorDash to show up, you'll just have to watch our students eat.
I'm all right. I'm going to have like airplane food in a couple of hours, so that'll be my consolation. But listen, thank you very much for having me. I really wanted to be there in person. I just couldn't make the travel work given some of the meetings this week and the trip to Europe. If there's ever an opportunity to come speak to you on site, I'd love to do that too. I'm often there on campus, so beautiful campus as well. So I never turn down the opportunity to visit if I can.
We'll take you up on that. Thank you so much.